Okay, so I'll be talking about long-range QKD with time and frequency. First with time, first with frequency, and then with hybrid time and frequency, and how that improves rates in in broadband solid-state memories like the ones we saw, we heard about in the tutorial in the morning, using AFCs. Yeah. Okay, so the contents were there for a slightly longer talk, but let me just tell you what, how I structured this. First, I'll explain the repeater architecture that we are analyzing, but our analysis in principle can be applied to other kinds of architectures, which especially use, don't use quantum logic in the sense that if it's only linear optics, then it can in principle be applied to that as well. So basically, after describing that, what we do is do an exact analysis and find the quantum state after a certain number of entanglement swaps. So you have the exact quantum state, which includes all the losses in the detectors and channel losses and dark clicks and all kinds of stuff. But I'll tell you what assumptions we make. And then using that state, you can do any number of things. And one of the things we do is find secret key rates and check the performance of those as we vary the parameters. So with dark clicks in the detectors, and we plot the rates. And then next we do some numerical simulations with source imperfections. That's something that we don't include in the analytic calculations, with source imperfections. And if I have time, I'll talk a little bit about our current work on using time modes to improve the rate envelope. Okay, so the repeater architecture is basically something that looks like this. So you have what's called an elementary link, the shaded region here, and you have quantum memories. So you have a certain distance, and you put quantum memories in there, and then in between two quantum memories or a quantum memory and the end is what we call an elementary link. And in the middle of an elementary link is a Bell state measurement. This is a linear optic Bell state measurement, which has a success probability of half if everything is perfect. So, and you have entanglement sources over here, where one half of it goes into the quantum memory, and the other half goes to the center of the elementary link. Similarly, in this quantum memory, there's one half that goes into the memory and one half that goes here. And these two halves that you get is a Bell state measurement that's performed, and you get an entangled pair across these two memories. But as discussed in the morning, in fact, there's frequency multiplexing that's possible. Because this Bell state measurement has only success probability of half, we can boost the success probability using the frequency multiplexing. So what happens is this state, the entangled pairs are created in many frequency channels, and halves of those goes into quantum memory, and the other half goes to the Bell state measurement. And if you have a lot of frequency channels like this, the success in one of them will happen with high probability. And that frequency, the successful frequency information, is sent back to both the quantum memories. Okay, so then similarly, say F1 works over here and some F2 works over here. This quantum memory has that, and this quantum memory has F1. And now these two quantum memories translate that frequency to a standard frequency, and they are now matched, and we can generate an entangled pair across the whole thing. And that's how this architecture works. So we basically analyze, what happens when you have this kind of thing where, this channel has losses, this quantum memory has, some inefficiency, and all the detectors are single photon detectors, but they can have dark clicks and inefficiencies. The only thing we assume is that the state is perfectly entangled. Excuse me, that there are no two photon terms. In dual rail basis, this is what the state looks like. And we also don't consider some other things like mode mismatch, which in principle can be done, but we don't do it in this analysis here. Okay, so more importantly, there's no purification done in this architecture, and so we don't have that. But still, as I will show you, it beats the repeaterless upper bound called the TGW bound. Even in spite of this, but the envelope is exponentially bad, as in it scales exponentially. But when you use time modes, it turns out that it can be sub-exponential, and I'll talk a little bit about that. Okay, so these are just the parameters that we use that I mentioned just now. Okay, so so what do we do exactly? So you have the elementary link, and when you do the Bell state measurement, and if it's successful, you have an entangled pair across the elementary link. Now you take two such pairs and then do a Bell swap, and you get another one. and take two such pairs and then bell swap. So you go in steps of two, powers of 2 like that. Oh, sorry. And at each level, with the state that we call is rho I. And that's essentially what we find exactly. So basically, if you take m plus as your initial state, it turns out that after any number of bell swaps, and the detectors, we have inefficiencies and dark clicks and everything, it still turns out that the final state is in the span of these psi 0, psi 1, psi 2, psi 3. Of course, there can be cross terms and everything, but it turns out that it's not an arbitrary state in this, but it turns out to be something that looks like this. Of course, we don't have to write it like this, but it turns out to be better if we pull out the m plus and m minus terms separately and the classical correlations separately. So AI, BI, CIDIs are coefficients that you get at the ith level. And because now if you take two such rho i's and you want to find rho I plus 1, you get some coefficients AI plus 1, BI plus 1, and so on, which can be calculated in terms of AI, BI, CIDI. That's not so hard to do. Once you have that, the point is now that we actually want, not in terms of the previous step, but all the way back to the beginning. So we actually want AI, BI, CIDIs in terms of the initial ones, initial AI, BI, A1, B1, C1, and D1. And such iterative maps, when you're given the coefficients at a certain level, you can find the next level. But then you can iterate like this, but then to go back to the initial stage is not so easy. And such iterative maps, in fact, show some strange behavior, like chaotic behavior. And this one's no exception, although we are not in the chaotic regime with those parameters. But it turns out that the map that's relevant to this is something called the logistic map. It's called the logistic map because it looks like this. This is actually the variant of the logistic map that we had to solve. But the logistic map itself is just Wi plus 1 is Wi times 1 minus Wi with some coefficient. It's called the logistic map because if you think of Wi as a bit, 1 minus Wi is it's not, and this looks like an and. It's not exactly that because Wi lies between 0 and 1, and it's not exactly 0 or 1. Now, if we assume that there are no dark clicks in any of the detectors, it turns out that we get exactly the logistic map, and we could use the solution of that to find out. But when we introduce dark clicks, we get this variant of the logistic map, which we were able to solve by modifying the ansatz by putting in a parameter and solving for that parameter. And then we were able to solve this particular one and get AI, BI, CIs, and DIs in terms of the initial A's and, of course, I. So this is what the solution looks like. And this is, won't tell you much, but then we were able to use these, coefficients, of course, to find the exact state and then plot the state in terms of, so we find the secret key rate using this formula and then plot that. So secret key rate ends up being, of course, in terms of the parameters of your detectors, the losses in your channel, and your memory loss. So once we find that, we can find the secret key rate and also the quantum bit error rate. So for example, if you do I swaps, and at that point, if you measure, if you have Alice and Bob over there, and they find out what the quantum bit error rate is, assuming they measured in the same basis, then you get QI. And then suppose you do the next level swap, and then if you find the quantum bit error rate, that's QI plus 1, and they turn out to be related by this quantity in this fashion. So you can find several things. I mean, we can also find the fidelity of the final state with some state that you hope to get. So it turns out that when you plot this, you get curves that look like, like this, which have three kind of different regimes. So these curves, the different colors are for different number of repeaters, where here we're going in powers of 2, so the number of, actually n is the number of elementary links, the number of repeaters is 1 less than that. But in terms of the number of elementary links, you have 1, 2, 4, 8, 16, and 32. And as you can see, this is the envelope, and this is what we want to focus on. For example, if you want to go up to 2,000, you wouldn't use 4. You would have to look at the envelope and then use the right number of repeaters at that point. So each curve turns out to have 3 different parts. There's this low loss flat part, and this is because we don't use multiple successes in the multiplexing. When you use multiple successes efficiently, then you get a slight improvement in this flat part. I'll tell you about it later. And this is the part that's due to the channel loss, which is exponential, and it makes the curve fall exponentially with distance. And this is the part that's due to dark clicks. When the fault due to resistance comes to a certain point, the dark clicks take over, and you get a cliff. So we could find out how dark clicks affect this rate loss envelope. One other thing that's kind of useful to find is Lmax, which is basically where this dark click cliff occurs. So if you fix the number of repeaters, what is the maximum length you can go up to with these repeaters where you hit this cliff? And that's given by this formula, which is in terms of the parameters in terms of detectors and losses and stuff. So as you keep increasing dark clicks, as you can see, dark click rates, as you can see, the cliffs start appearing closer and closer earlier, but the envelope doesn't change. It's still the same. But of course, if you increase it by a lot, even though the envelope doesn't change, there is no curve over here. So you'd have to go down to a large number of repeaters, and your initial rate itself will be very low. So there's not much point doing that. So dark clicks affect the cliffs, but then not the envelope, but up to a certain point. OK, so this is what we did analytically. Then we started doing numerical simulations to find out how two-photon or multi-photon errors affect the rates. So the state that we consider is something that's a truncated SPDC, two-mode SPDC state that looks like this. With the probability P1, you have the right state. With probability P2, you have the two-photon term state. And then 1 minus P1, P2 is the vacuum. So we fixed P1 to be 0.9, and then started varying P2. And as P2 increases, we found, somewhat surprisingly, that it's really, really detrimental. In fact, if you have P2 to be really, really small, I mean, this is nowhere near the SPDC kind of thing where P2 is square of P1. So even P2 is extremely small. It turns out that, little n here is log of capital N. So this n equal to 3 is 8 elementary links. That's 7 repeaters. It turns out that 7-repeater curve crashes in the sense that it's below this, it's completely inside these other ones. In other words, at no distance at all, there's any point in going to 8 repeaters. You never have to do that because you never get any improvement. So if you increase P2 even more, at some point, n equal to 2 crashes. So there's no point going up to 4 repeaters. You never get any improvement. And finally, if you keep increasing it even more, even n equal to 1 crashes. So finally, you're left with n equal to 0. That's 1 elementary link and no repeaters. So eventually, having no repeaters with this much P2 is what you'll have to do. OK, and then this, let me skip over this. This is the part where we tried to incorporate the P2 effect analytically to get the exact calculation done for P2. And we found some interesting connections. But I want to move to the next part, where suppose we do want to use SPDCs, then what can we do in this architecture to get back the rates that we had, or at least slightly better than the ones we saw just now? So for that, we noticed that actually, so if you use SPD, single photon detectors, then as we saw before, even with a small amount of P2, nowhere near SPDC kind of P2, but a small amount of P2 is very detrimental. But if you replace those single photon detectors with PNR detectors, even those PNR detectors have losses and dark clicks, but still, they can weed out some of the P2 higher photon terms. So then you get back the rates if you can improve the multiplexing by a factor that's proportional to your P1 squared, actually. So if you can multiplex even higher, then you can get back the rates that look pretty much same as that for the deterministic sources. And in fact, in particular, beat the TGW bound and get back rates that are still exponential in distance, but can beat the bound. So this is here, because it's numerical simulations, we went sequentially, number of elementary links. And for this, it's exponential, but then the exponent is better than that, that for the TGW bound. And this is, the parameters for this rate loss. And finally, I want to talk a little bit. Oh, so yeah. So let's. This is the part where we take into account multiple successes at the elementary links. So as I mentioned, there's many frequency channels, and if you have a lot of them, the probability that at least one of them is successful is very high. But then, in general, you can get more than one success. And in the previous slide, in the previous plots, we weren't using those multiple successes. But if you do use them, it turns out that you get an improvement only in the flat part of it, not so much the rest of it. So in the low loss regime you can get a little improvement. So this is nice, but you can do better if you use time modes. So if you have hybrid frequency and time, then you can actually get sub-exponential scaling. So we were able to show this analytically. If you instead of getting e to the minus something times L, you get e to the minus square root something times square root L. So this is, of course, something where we're assuming that in the time mode switches, there isn't any loss. To prove this, we assume that. If you have small amount of loss, it's probably okay, but we are now looking into finding the threshold of that loss, which makes this thing go exponentially bad. So here there are frequency modes, 100 frequency modes, and the time modes keep increasing. If you increase the time modes up to a certain point, when there's no loss, it's very good, actually. So you get this sub-exponential scaling. OK, so I'm kind of out of time. So essentially, what we've done is look at the exact analysis with dark licks and all kinds of inefficiencies in the detectors and channel loss and everything. But when the initial entangled quantum state is exactly, it doesn't have two photon terms. In that case, single photon detectors are fine, and you get a very good rate that beats TGW bound. But then if you want to use SPDCs, single photon detectors are pretty much out of the question, and you have to use PNR detectors. And it turns out that they actually give you back the rate if you can multiplex a little bit higher. And finally, with lossy devices too, you can get sub-exponential rate loss scaling if you can use time modes. But with switching loss, again, that comes down, and we are now working on how to find out what threshold of switching loss it can tolerate. Yeah, so with too much switching loss, it goes back to the exponential scaling. OK, thank you.
Do you have any questions on this talk? Yes.
So the question is about the sub-exponential scaling.
Mm-hmm.
How the optimal number of repeater stations scales with the distance?
So optimal number of repeaters. So I mean, from this envelope, you can kind of find out, but we don't have a formula for it.
Okay.
But if you plot the envelope, we basically have a formula for the rate with the other parameters from which we can, in principle, find out. We do have that formula for the deterministic sources and single photon detectors plots that I have before. For this, we're still in the process of working on the formulae for this. Right now, we have only this. Yeah.
Are there other questions? Well, if not, I'll declare the session over. Let's thank Hari and all the speakers, and then we're going to go to lunch.